Hey folks, this lesson will help you get ready for your upcoming Chapter 5 test in statistics on normal probability distributions. All right, so here we go. In a recent year, ACT test scores that are normally distributed excuse me, had a mean score of 21.1 and standard deviation of 5.3. The test scores of 4 students are randomly selected are 15, 22, 9, and 35. Find each z-score and determine whether any are unusual. Okay. So remember the 68, 95, 99.7 rule. 68 is one standard deviation away. 95% of the data is within 2 standard deviations away. So that means anything past 2 standard deviations away is less than 5% of the data. So anyway, so when we get our z-scores, those are our standard deviations right there. So, and then this says it's normally distributed. So even though we have a sample of only 4 students, any population size or sample size will be normally distributed also, as long as it's normally distributed. Okay. So there's our z-scores right there. Remember, z equals x minus the mu divided by the standard deviation, and x is all of these numbers. So these are all our x's. Okay, so our unusual ones are the ones that are more than 2 standard deviations away. So -9 is unusual, and 35 also, because they lie more than 2 standard deviations away from the mean. Okay, so let's draw a normal curve with a mean of 60, standard deviation of 12, and describe how you construct the curve. Okay, I did miss something in here. I wanted to say on here, so you draw a normal curve, you guys, and your mean goes right in the middle, and then plus 12, plus 12, plus 12. We should have added another 12 right there. Okay, so that would be like 96, and then minus 12 is 48, minus 12, and then minus 12 would be over here at like -24. Okay, so that would be 3 standard deviations to the right and 3 standard deviations to the left. And there are these inflection points. They're right about here-ish, and right about, I should have made it a little bit bigger here, right about here, and right about here when we go 1 standard deviation to the right and to the left. So it goes, this is called concave up, and then it goes concave down. It cups down. Concave up is where it cups up, and so at 1 standard deviation from the mean on both the left and the right is where it changes from concave up to concave down. Those are the inflection points. All right, so a student indicates that for each trip to the supermarket, a survey, sorry, a shopper spends an average, there's our mean of 45 minutes with a standard deviation of 12 minutes. The length of time spent in the stores are normally distributed. There's our magic word, normally distributed, and are represented by the variable x. So a shopper enters the store. Find the probability that the shopper will be in the store for each interval of time listed, and then interpret that answer when there's 200 shoppers in the store. Okay, so the first one is between 54 and 24. Okay, so here's our curve that shows a normal curve. Whoops, that should be a V right there. Right there, our normal curve. Let me get the V in there, and it's going to say C in there for the rest of them, with the mean 45. So here's our mean right there, 45, and our standard deviation of 12. So minus 12, minus 12, minus 12. Okay, so I should have wrote the right numbers on there. If that's 45, 45 minus 12 would be 33, and 33 minus 12 would be 21, and so on. And 21 minus 12 would be what's that? 9, I think. So anyway, and then we'd go plus 12, plus 12, plus 12 to the right also. Okay, so here's the area between 24 minutes and 54 minutes right there. Okay, all right. So let's see, it says curve with the C, sorry. So here's our z-scores right there for 24 and 54, okay? So the probability the shopper will be in the store between 24 minutes and 54 minutes is the probability that x, our random number x, is between 24 and 54. It's going to give us the same as our z-score between -1.75 and 0.75, okay? So that equals, we subtract those two, the bigger one minus the smaller one right there. So we look up our standard deviation of z-scores of 0.75, and we get 77.34. 0.7734 minus 0.0401, and we get 0.7333. Okay, now it says, now interpret the answer when there's 200 shoppers. So here's the probability. Found the probability that the shoppers will be in the store between that right there, and then with 200 shoppers, we just take that probability and multiply it by 200, and we get about 147 shoppers in the store between 24 and 54 minutes. Okay. All right, how about more than 39 minutes? Okay, so here's our graph right here, and more than 39 minutes is going to be z-score with a negative 0.05. And so here's the graph, more than is to the right. So it's going to be 1 minus the area to the left of 0.5, because remember our standard normal curve is to the left. Boy, I'm misspelling. I did this early in the morning this morning, and I can see I misspelled a bunch of stuff right there. Anyway, so we look up negative 0.5 on there, and we get our answer to be 0.6915. Okay. All right, so interpret. So if 200 shoppers enter the store, then we multiply 200 times 0.6915. So about 138 shoppers will be in the store for more than 39 minutes. Okay. All right, scores for the California Peace Officer standards and training tests are normally distributed with a mean of 50 and standard deviation of 10. An agency is only going to hire applicants that have score in the top 10%. So what's the lowest score somebody can earn to be still eligible to be hired for the agency? Okay, so the top 10% means over here. So if this is the top 10%, then this is the bottom 90%, and that's where we get our z-score for the bottom 90%. We're looking for our x value that gets us this. So what z-score gives us a bottom 90% right there, okay? So look up the z-score that corresponds to a cumulative area of 0.90, and I see one in our standard normal table of 0.8997. So we get a z-score of 1.28 right there. Okay, so now we're looking for x. So z equals the mean divided by the, or x minus the mean divided by the standard deviation. So we plug in 1.28 in our mean and our standard deviation, multiply both sides by 10, and then add 50. Okay, so, boy, I don't know what I did right there. I think that word problem just slipped down. Yeah, okay. So, so we get about 62.8. So let's answer the question. So the lowest score you can earn and still be eligible would be to get a score of about 63. All right, okay, so this graph shows the length of time people spend driving each day. You randomly select 50 drivers ages 15 to 19. What's the probability that the mean time they spend driving each day is between 24.7 and 25.5? Assume that standard deviation is 1.5. Okay, I don't see anywhere in here that says normally distributed. So the only way for our central limit theorem to work is if our sample size is greater than 30. And since 50 is greater than 30, then we can use the central limit theorem to conclude that the distribution of the sample means is going to be approximately normal. Okay, and so the mean and standard deviation, the mean is the same as the population mean right here, but the sample standard deviation is we take the population standard deviation and divide it by the square root of n in this case being 50. All right, now if you're taking the AP test, they will want you to state that the central limit theorem will let us use this and conclude that our sample mean distribution is going to be approximately normal because the sample size is greater than 30. Okay, now if it said it was normally distributed, then we can have smaller sample sizes, but if it doesn't say it, then it has to be greater than 30. Okay, all right, so the mean right here, where does 25 minutes come from? Okay, drivers age 15 to 19. Here's 15 to 19, their average time is 25 minutes. That's where we get this 25 from this chart right here. Okay, all right, so 1.5 divided by the square root of 50 is about 0.21213. Okay, all right, so let's get our curve written. So here's our curve. Here's the mean, 25, between 24.7 and 25.5. So we always write the title, mean time in minutes. And so here's the graph with the shaded area between 24.7 and 25.5. Okay, so the probability is going to be whatever our z-scores is between these two numbers right here. Okay, all right, so Let me just slide that up. So the probability of the mean time the 50 people spent driving is between 24.7 and 25.5 is this, where our x is between those, which is equal to the same as our z-scores between these two z-scores, okay? And then when it's between, we take the bigger z-score and we subtract off the area for the smaller z-score, okay? So that gets us about 91, a little over 91% of the time. So interpretation of the sample of 50 drivers aged 15 to 19, about 91% will have a mean driving time that is somewhere between 24.7 and 25.5 minutes, okay? This implies that assuming the value of the mean 25 minutes is correct, about 9% of such sample means will lie outside the given interval. All right. Okay, so here we go. So 58% of adults say they have never worn helmets when they ride bikes, or they never wear helmets. Okay, so you randomly select 200 adults in the U.S. and ask them whether they wear a helmet riding bikes. What's the probability that at least 20 adults, 120 adults, will say that they have never worn a helmet when riding a bike? Okay, so this is either they say yes, they wore a helmet, or they don't. So it's binomial. There's two choices right there. Okay, so it does not say it's normal in this population right here. So the only way we can conclude it's normal is if NP is greater than 5 and NQ is greater than 5, and both of them are greater than 5, so our binomial variable is going to be approximately normal. Okay, so the mean is equal to NP, which is 1/16, and the standard deviation is going to be the square root of NPQ for these binomial distributions. Okay, remember that? So we get those values right there. Okay, so we can use the continuity correction. We can rewrite the discrete probability, which is greater than or equal to, because it says at least, as the continuity probability that we take off 0.5. Now, if it just said greater than that, then we'd have to go to 120.5. But this says at least, so it's greater than or equal, so we go to the left 0.5. Okay, that's our x that we plug in for our z-score. So here's our figure. This shows a normal curve with a mean of 1/16, standard deviation of 6.98, and the shaded area to the right of 119.5. Okay, so here's our z-score. We got to calculate that, and we get about 0.5. So the probability that at least 120 adults will say that they never wear a helmet is about, it's going to be the probability that it's greater than that, which is going to be the probability that z is greater than 0.5, which is 1 minus that, because our table always gives us to the left right there. So we get about 0.3085, okay? And that's what they're asking. What is the probability that at least 120 adults will say they never wear a helmet? About almost 31% of the time, okay? All right, if you're sitting in my class, I'm going to have you guys working on that. Take care.